Hey dudes, Dude the Builder here, and in this episode of Zig in Depth, we're going to be talking about the ArenaAllocator. The main difference between the ArenaAllocator and other allocators is that with other allocators, you normally allocate and deallocate during the lifetime of your program, the execution. Whenever you need something, you allocate, and whenever you don't need it, you deallocate. Well, with the ArenaAllocator, the strategy is different in that the way it works is that you allocate memory, but you don't deallocate only until that point in the program, usually at the end of execution, when you deallocate everything all at once, okay? So basically the ArenaAllocator, it's like it keeps a record of all the allocations that you make, and you don't have to be deallocating during your program. You just wait till the end of the program or the end of a certain period where you no longer need any of those allocations, and you call the dinit method on the Arena, and that will free all of the allocations all at once, okay? So this can have a really big impact on the performance of your program, because it basically eliminates the overhead of allocating and deallocating constantly. So it can be beneficial when you have many allocations in a short-lived program, or in a short-lived portion of a cyclical program. For example, if you have like a command line application that runs, has a short lifespan from start to finish, and then it exits, then this is a good candidate for that type of application, because you can just allocate all you want during the execution, and then it'll free everything when you're ready to exit. Also, if you have like a web server and, for example, a request handler, you can have an arena for each request handler, and you allocate everything that you need. Once you serve the response, you can free all the allocations all at once. If you have, on the other hand, a long-running process, for example, like a daemon in the Unix world that's going to be running forever, maybe an arena is not a good idea, because all those allocations are going to keep stacking up in terms of memory use. So you could possibly reach an out-of-memory situation with an arena. So for that type of application, an arena, maybe it's not the best fit, okay? I'm going to be demonstrating one other instance where an ArenaAllocator is really good is when you have recursion mixed with allocation. And I'm going to be basically showing an example of that. I'm going to be showing an example of a simple linked list implementation. It's not a complete implementation. I just implemented enough to demonstrate the difference between normal allocators and the Arena. This first version that we're going to be looking at is the version that uses a normal allocator that you pass in. As you can see, it's a generic implementation using a function that called list. It will return the type, which is a struct. Within that struct, we have here the node type for the list, which basically represents each item in the list. And here we have an example of what I mentioned previously, where we store in a field a copy of the allocator that we're going to be using for this data type. And this allows us, when we have to free the resources, we can use this copy of the allocator. And we have the data field, which will hold our data for each element in the list, and the next field, which is an optional pointer to the next node. Okay, so here we see the recursive nature of this data type. It's referring to itself through a pointer, through a level of indirection. Here we have the traditional init method. When we are making use of allocators, we receive an allocator and the first data element. That's going to be the first element in the list. And what we do is we try to create a pointer here for our node, and we assign the allocator field, the data field, and we set the next field to null, and we return that pointer. Here in the init, what we're going to do is we have to make sure that all of the next elements in the list following this one are also going to be de-initialized, because through this element, it's the only way that we can access those other elements. Okay, that's basically the nature of the linked list. So if we have a next item, we capture that pointer and we call the-init on that pointer. And this the-init will once again, it'll recurse basically. If that other item has a next, it'll call the-init on its next, and so on and so forth, until it gets to the end of the list where the last item has a null next field. Finally, once we do that, we call the destroy method on the allocator for ourself, which is a pointer to a node, okay, which is basically this pointer that we created here. Okay, so we're freeing that memory. Now here we are on the list itself. We are once again storing a copy of the allocator. We are here establishing with the head field the first node, a pointer to a node in our list. And here we have the init method for the list itself. We're passing an allocator, once again passing the first data item, and we set those fields here. The head, we create the first node, and when we call the init, we call the init on the head of the list, because given the recursive nature, calling the init on the head will then proceed to call the init on all the other linked items in the list. So this is basically the spot where we're going to get a lot of deallocations happening at the same time. Okay. Now we have the append method. This is how we add items to the list. And basically what we're going to do is we have to find the tail of the list, which would be the item that has null for the next field. We do that with this while loop here. And when we find it, we then create a node with node.init and put it in the next field of the tail. And this new node will have null for its next field, so it's a proper new tail for the list. And here we have a lookup method that takes the data of the type that we're working on, and basically we use the same recursive method starting out at the head, and we use the while as an expression here with its modality checking an optional here. Current is an optional pointer to a node. And if if it isn't null, we capture the pointer and we check if it's equal to the data that we're being passed in. If it is, we break true. If it isn't, we continue by assigning its next field to current. And if we reach the end of the list, we return false. Okay, so it's a pretty simple linked list implementation using a normal allocator. Now we're going to go to our main file, and what we have here in main is pretty much a little benchmark. We're going to be benchmarking the performance of this list, and as you can see here, I'm importing the version that you just saw is this one in list.zig. This one is going to be the one with the arena. We're going to be looking at that in a while. And the first thing we're going to do is we're going to set up the allocator that we're going to be using. Up till now, we've been just running tests in previous videos, so we were using the testing allocator. But here, since we want to run this benchmark in main, we have to use one of the production allocators, if you will. And the most general purpose allocator, and that's the name that it's given in the standard library, the general purpose allocator that we have at our disposal, is just that. It's an allocator that's designed to work in pretty much any type of situation. It's not tuned for any specific strategy, like for example the fixed buffer allocator or the arena, like we're going to see here. So overall, in your normal Zig programs, if you don't have any special situation that requires a special allocation strategy, you should be using this type of allocator. Another benefit of the general purpose allocator is that when you're in debug mode or in release safe, which we're going to be talking about release modes later on, it'll provide also, as we saw with the testing allocator, it'll detect memory leaks, okay, automatically. Okay, so here we create an instance of the general purpose allocator. What we have here, this is the empty tuple syntax. The thing is that when we create a general purpose allocator, we pass in a configuration object, but we're not going to change any of the configuration, so we pass in like this empty tuple. It's representing like an empty object. And then these other braces are basically actually creating an instance, because general purpose allocator here is a generic function, okay? So once we call that function, it creates the type, then these braces create an instance of the type. And here we are calling defer with the deinit of that general purpose allocator, because it has some internal state that it has to free once you're finished working with it. This deinit doesn't free the allocations, the actual allocations, as we're going to see with the ArenaAllocator. This is just for the state that the allocator, the general purpose allocator, uses itself. And here we're once again calling the allocator method on the GPA to obtain the actual allocator instance, okay? We have this part here commented out because that's what we're going to use with the arena. And what we're going to do here is we're setting up a couple of constants that we're going to be using. First, the number of iterations that we're going to be using in this benchmark, and the number of items that we're going to be creating in the list for each iteration. Here we have an example of a timer that we have in the standard library, which allows us to measure the elapsed time within our programs. And here is our main loop here, where we're going to loop the number of iterations. And in each iteration of this loop, we're going to be creating a list. We are going to be adding the number of items, the item count total to that list. And then we're going to be deallocating or deinitializing the list with its deinit method. Okay, so basically in the case of our normal linked list here, it's gonna is going to be pretty much one of the areas where there's going to be a lot of memory activity in deallocating all of the items of the list one after the other. Okay, and then finally we basically measure the elapsed time, dividing it here by nanoseconds per millisecond to obtain it in a millisecond, a more friendly format, and we report how much time it took. Okay, so let's go to our other terminal and let's run this. And let's wait here. Okay, here we go. We have that it took 2,889 milliseconds approximately, so about 2.8 seconds. Let's run that again, see if we have a pattern here. Okay, second time 2,800, so it's pretty much 2.8 seconds. Okay, now let's look at our ArenaAllocator version of the linked list. Here we're going to see it's pretty much very similar to the other linked list. That's one of the benefits of the allocator interface in Zig, that each allocator is pretty much a drop-in replacement for the other allocators. The interface is pretty much the same. So here in our node, we're not going to be storing an instance of the allocator because we're not going to be calling deinit on the node. Okay, we're going to be freeing everything when we call deinit on the arena itself. Here our init method is pretty much the same as we saw previously. Okay, in terms of the list, the big change that we're going to be seeing is that instead of storing stud mem allocator, now we're storing the arena itself, which is a stud heap arena allocator. Okay. We will be receiving in the init method for the list a normal allocator, a stud mem allocator, and that's going to become what's known as the backing allocator or the child allocator of the arena. And we see it here when we initialize arena with the init function, and we pass in the backing allocator. So what we can tell from this is that in Zig, arena allocator is basically a composition. It's composing allocators here. The arena is using itself another allocator, and the arena allocator will then implement its allocation strategy over the child allocator that it will be using as its backing allocator. Here, once again, everything pretty much stays the same. The thing is that instead of returning directly the initialization, we first have to assign it to a variable here, because we need the arena to be initialized first. So then when we're going to create the new node here with init, we need to call the allocator method of the arena, okay? And that gives us the actual allocator instance. And then we return the list, okay? And aside from that, everything stays pretty much the same, except that when we, for example, anywhere that we need an allocator, instead of accessing directly an allocator field, we call the allocator method here of the arena field of the list. The way that the allocator interface works is anytime that you call this allocator method on the same instance of an allocator, you're going to receive the same allocator, okay? So it's safe to do this, okay? And everything else stays pretty much the same. So in order to use this version of the list in our main file, we are going to comment out this one and uncomment this one. We are not going to be using the general purpose allocator here. We will be using as the backing allocator another allocator, which is the page allocator. It's important to note, I've seen videos and tutorials that use the page allocator directly as an allocator, as we're using the general purpose allocator up here to make direct allocations in programs. And that is really not recommended, okay? The page allocator, each time you allocate, even if you just need 1 byte of memory, it's going to allocate a whole page of memory. And pages of memory, depending on your environment, can range from 512 bytes up to all the way to 8 kilobytes, okay? So it's really not an efficient allocator for small allocations. The main purpose of the page allocator is, if you're designing yourself an allocator, then you can use the page allocator as a backing allocator, which is what we're going to do here with the arena allocator. We're going to use it as the backing allocator of the arena, okay? So that's an important little note on the page allocator. And since, as I said, the interface for allocators is pretty much the same, we don't have to change anything else in our main file here. So let's go back to the terminal and run this. And as you can see, we see a pretty big difference here. It's only 121 milliseconds. Let's run it again to make sure. And yep, now it's 82 milliseconds. So you can see that the difference between using directly an allocator to allocate and deallocate a lot of items, as we were doing with the general purpose allocator, versus using an arena allocator, which deallocates everything all at once, all at the end, can have a major impact in the performance of your program, okay? So as you can see, the choice of allocator, depending on the use case, can have a significant impact in the performance of your application. And the ArenaAllocator is the good choice when you have lots and lots of allocations and you have a short-lived program or a portion of your program that makes use of some resources, and then you can free them all at the same time when you're finished. The ArenaAllocator is definitely a good choice for that type of situation. Okay, so I hope you find this useful. Do the builder here. I'll see you in the next one.